In this subsection, we will analyze Tonelli-Shanks algorithm and present it differently as usually seen. We'll derive a Tonelli-Shanks formula and then compare this method with the infinite descent method just seen before. Tonelli-Shanks algorithm can be challenging to grasp initially, as it requires some theoretical understanding. However, with a few examples, the computations becomes more straightforward. The algorithm leverages the property of the multiplicative order of n modulo p, that is, the smallest positive integer k, such that n raised to k is congruent to 1 modulo p. When a and b that are co-prime to p and both having order 2 raised to j modulo p, given that a raised to 2 raised to j is congruent to 1 modulo p, then a raised to 2 raised to j minus 1 is not congruent to 1 modulo p, because 2 raised to j divides p minus 1. So a raised to 2 raised to j minus 1 is congruent to minus 1 modulo p. The same logic applies to b. So b raised to 2 raised to j minus 1 is congruent to minus 1 modulo p. Consequently, a times b raised to 2 raised to j minus 1 is congruent to 1 modulo p, indicating that a times b has order 2 raised to h modulo p, where h is smaller or equal to j minus 1. Given that p minus 1 equals m times 2 raised to k, where m is odd, for an integer x, we have x raised to m raised to 2 raised to k equals x raised to p minus 1, and that is congruent to 1 modulo p because of Fermat's Fiedel theorem. When x is a quadratic non-residue, then x raised to m raised to 2 raised to k minus 1 equals x raised to p minus 1 over 2, which is congruent to minus 1 modulo p. Thus, the order of x raised to m cannot be smaller than 2 raised to k. In fact, its order is exactly 2 raised to k. When x is a quadratic residue, the order of x raised to m divides 2 raised to k. By repeatedly squaring x raised to m, we can accurately determine its exact order. The key point is that when x is a quadratic residue, x raised to m raised to 2 raised to k minus 1 is congruent to 1 modulo p, indicating that the order of the quadratic residue is smaller than the order of the quadratic non-residue. So by combining a quadratic residue and a quadratic non-residue within this framework, we can reach the solution in a finite numbers of iterations. Let's now unpack Tonelli-Shanks algorithm. This algorithm is typically introduced as a straightforward recipe, outlining a series of steps to reach the solution. However, what is missing is a clearer display of its mathematical building blocks. When trying to determine the modular square root, x squared congruent to n modulo p, where n is a quadratic residue and p minus 1 equals q times 2 raised to k, where q is odd, Tonelli-Shanks algorithm cleverly starts by setting the square of n raised to q plus 1 over 2 congruent to n times n raised to q modulo p, plus finding a quadratic non-residue z modulo p, whose order z raised to q is 2 raised to k. Next, find by checking values the order of 2 raised to k sub 1 of n raised to q. That is, the smallest k sub 1 bigger than 0 and smaller than k, such that n raised to q raised to 2 raised to k sub 1 is congruent to 1 modulo p. Once found, we apply z raised to q times 2 raised to k minus k sub 1 on both sides of the congruence. Next, proceed with squaring and determine by checking values the order of 2 raised to k sub 2 of n raised to q times z raised to q times 2 raised to k sub 1 minus k sub 2. That is, the smallest k sub 2 bigger than 0 and smaller than k sub 1, such that it raised to 2 raised to k sub 2 is congruent to 1 modulo p. Then apply z raised to q times 2 raised to k minus k sub 1, all of which raised to 2 raised to k sub 1 minus k sub 2 on both sides of the congruence. We'll need to repeat the procedure until the product of brackets at the right side are congruent to 1 modulo p, thus reaching the solution. This procedure might seem rather messy because the numbers get really big when the algorithm requires further iterations. You can always apply modulo p to the values and work with smaller numbers, which is the usual approach, by the way. But there's something to be learned by not applying congruencies and instead linking up the powers. This approach enabled us to discover a Tonelli-Shanks formula. Let's proceed step by step. First, consider a case that requires only one step to reach the solution. On the left side of the congruence, the exponent of z is q times 2 raised to k minus k sub 1 minus 1, which is equal to q times 2 raised to k minus 1 over k sub 1. Since q times 2 raised to k minus 1 equals p minus 1 over 2, we can simplify the expression. Therefore, the exponent of z is p minus 1 over 2 times 1 over 2 raised to k sub 1. The same reasoning applies to the right side of the congruence. Next, we apply the same procedure for a case that needs 2 steps to reach the solution. Note that the gray block simplifies into z raised to q times 2 raised to k minus k sub 2. This reveals that in step alpha, we are applying to the exponent of z the product of q times 2 raised to k minus k sub alpha. When combining this, the exponent includes the sum of the reciprocals of 2 raised to k sub 1 and 2 raised to k sub 2. When dealing with these steps, the solution involved the sum of the reciprocals of 2 raised to k sub 1, 2 raised to k sub 2, and 2 raised to k sub 3. Therefore, when m steps are needed, the exponent includes the sum of the reciprocals of the separate k sub m values. Remember that k sub 1 is smaller than k, that k sub 2 is smaller than k sub 1, and so on. Finally, as the brackets on the right side are congruent to 1 modulo p, the Tonelli-Shanks formula is revealed. We should clarify that this formula doesn't offer a significant advantage over the algorithm, as computing the k sub m values still involves dealing with the previous figures. However, this formula provides a clearer view on how these multiplicative orders 2 raised to k sub m play in the final result. Let's see an example. Let's find the modular square root of x squared congruent to 41 modulo 769. We check that 41 is indeed a quadratic residue of that prime, and by checking values, we find out that 7 is the smallest quadratic non-residue. Next, we apply the initial equation provided by Tonelli-Shanks algorithm. It involves 41 and 3, the quadratic residue, and the odd quotient of 769 minus 1. Then we know that 7 raised to 3 has order 2 raised to 8, as 7 is a quadratic non-residue. So 7 raised to 3 raised to 2 raised to 8 minus 1 equals 7 raised to 769 minus 1 over 2, which is congruent to minus 1 modulo 769. Next, we need to find the order 2 raised to h of 41 raised to 3. And here we need to check a short list of values, as h is smaller than k. We find out that h equals 6. And so we can apply 7 raised to 3 raised to 2 raised to 8 minus 6 on both sides of the congruence. We check that 41 raised to 3 times the value we just applied is not congruent to 1 modulo 769, so we need to square again. The next step is now computing the order 2 raised to I of the bracket on the right side of the congruence. We find that I equals 3. Thus, we apply 7 raised to 3 times 2 raised to 8 minus 6 raised to 2 raised to 6 minus 3 on both sides of the congruence. This time, we check that the product of the two brackets at the right side of the congruence are congruent to 1 modulo 769. So we reach the solution. Note that the solution can be expressed more clearly with the Tonelli-Shanks formula. The usual way of Tonelli-Shanks algorithm is to work with residues modulo 769 at each step, as seen with the numbers in gray, thus reaching the solution. 612 squared is congruent to 41 modulo 769. We could also apply the formula previously derived and reach the same solution, as seen in yellow. Yet, to make the formula work, you need to derive the order 2 raised to h and 2 raised to I, and you can't do that if not going through the algorithm. Beforehand, you cannot know how many multiplicative orders 2 raised to k sub m you'll need to compute. The only thing we can say beforehand is that once you compute the value of h, which is equal to 6, the sum of the reciprocals of the order lies in the range 1 over 64 to 63 over 64. So the formula doesn't really give an advantage over the algorithm. Nevertheless, it nicely shows how those k sub m values impact in the method. Well, let's now get back to the infinite descent method developed previously and check how it performs for the same case. Press pause if needed. In this next slide, you can see a summary of the steps involved in Tonelli-Shanks algorithm and the infinite descent method. Tonelli-Shanks algorithm relies heavily on the multiplicative order of 2 raised to k modulo p, while the method developed in this presentation starts with a variation of Nevin's congruence and uses infinite descent to find the solution. Despite the different approaches, the outcome at each step are quite similar. In some cases, the first method can act like an infinite descent or an infinite ascent, as seen above, but this is not always the case, as shown in the case below. Both methods require roughly the same number of computations. The first one involves large numbers and computing orders 2 raised to k sub I modulo p, while the second involves checking divisibility at each step of the factors of m raised to 2 raised to u plus 1 minus n raised to 2 raised to u. Perhaps we could only add that with the infinite descent, the steps are clearer, and from a mathematical point of view, it's a simpler method. In summary, this section extends Nevin's congruence procedure for primes of the form 8k plus 1, effectively establishing a twin infinite descent protocol for determining whether such primes can be represented as x squared plus minus n times y squared. The initial infinite descent involves adapting Nevin's congruence for primes of this form to determine the modular square root. The second infinite descent employs the simple descent method to find out whether the primes possesses the desired representation for a given n. The most extreme cases for this twin infinite descent protocol are Fermat primes. Later, we analyze Tonelli-Shanks algorithm, offering a clearer display of its mathematical building blocks. This analysis allows us to derive a Tonelli-Shanks formula. While this formula does not provide an advantage over the usual algorithm, it offers insight into the role of the multiplicative order in finding the modular square root. Finally, we compare Tonelli-Shanks algorithm with the infinite descent method. Despite the different approaches, the outcomes at each step are quite similar, and both methods require roughly the same number of computations. To conclude, throughout these 11 sections, we have meticulously outlined a comprehensive procedure for identifying the representation x squared plus y squared for primes of the form 4k plus 1. Additionally, we have derived methods for determining the existence and actual values of representations x squared plus minus n times y squared for primes of the forms 4k plus 3, 8k plus 5, and 8k plus 1. In doing so, we have effectively covered the entire spectrum of prime numbers. But there's more. We still have two appendices to share involving Gauss cyclotomic formula, how they can be derived utilizing elementary tools and applied for the representation of primes, plus multiple representations involving Lucas and Fibonacci polynomials.